Okay, let's go over. I don't see Hannah or Chad. All right, we are going to talk about, well, one thing we would have talked about we did talk about for a very brief time last class period. We would have talked in more depth last class period. And then one that is coming up in the coming week in general physics. So one thing will be ahead of general physics here that we're talking about. So the two things I'm talking about, since words escape me, are the center of mass and moment of inertia calculations. So we've already seen the center of mass. Notice this picture has the word center of gravity. Our textbook likes to use the word center of gravity a lot more than it likes to use the word center of mass. What's the difference in center of gravity and center of mass? Yeah, not much. As long as you're standing here on the surface of the earth and you're of a reasonably small size, there is no difference. The technical difference is the center of gravity is the point at which you can treat the force of gravity as acting. And the center of mass is the calculated, essentially average position of the mass. If the acceleration of gravity is constant throughout the entire body, then the two are exactly the same thing. If the acceleration of gravity is changing through the body, then they're going to be different. So for anything that we're going to be doing that deals with something of reasonable size, not enormous size, on Earth, the two will be the same. So we tend to use the terms interchangeably. Question?
So if the center or if the acceleration of gravity is changing, it has to be big enough to actually have a notable difference in distance?
Yes. Yeah.
But then the acceleration is different?
Yeah.
So we're talking really big.
Yeah, exactly. All right, so we've already seen the equation for center of mass calculation, and we've seen the calculus version. The non-calculus version, you have a summation over all of the pieces of mass in an object. So you're saying, okay, something like I have little boxes. Each box has a certain mass in a certain position. And on the top, I'm adding up the mass times its position. On the bottom, I'm just adding up all of the masses. We have physics versions of these that are calculus versions of these, because most objects are continuous objects, right? You don't have something like U made up of a whole bunch of little boxes. As far as we can tell when we look with our eyes, you are continuous. Now, of course, if you get really, really specific, you would say, oh, no, there's an atom here and an atom here and a space in between. Well, we're not getting that tiny. So to change these to calculus forms, we just put an integral instead of a summation. S for sum, sigma, the Greek letter for sum, x dm. That was what we have already done. For moment of inertia is a different idea. Moment of inertia is the rotational equivalent to mass. Now, that sounds kind of funny. You have a mass. I have a mass. And my mass is going to be just measuring how much stuff is present in me. But when things are rotating, the rotational equivalent of mass, the moment of inertia, or rotational inertia, you'll find different names. You who are engineering students probably have yet another name. But that rotational inertia has to do with where the mass is located as well as the mass. So if you have a mass far from the axis it's rotating around, it acts as if it has a bigger rotational mass, bigger moment of inertia, than if that mass is close to the axis. And so the mathematical relationship is the moment of inertia is the sum of each piece of mass multiplied by the distance from the axis of rotation squared. So this r has to be distance from the axis of rotation. So let's take as a simple example, I have this mass and I'm going to have it go around my body. Okay? So the axis of rotation is the axis going through my head. What difference is it going to make to the moment of inertia if I hold the mass here or if I hold it down here? Okay, I see a lot of people shaking their heads. No, meaning no difference. Why does that make no difference? It's only the distance going away from the axis that matters. So going like this, then I have a bigger r. If I double the r, then my r squared is 4 times bigger. And that's why, well, we'll learn that in physics, but that's in the algebra class on, well, Friday or Monday, whichever day it comes up. But that makes a big difference for rotation. Now, if we want to take this equation and write it as a calculus equation, how do you suppose it would change? Okay, like this except for one thing. We do put a perpendicular sign here now. We're very specific, saying it's the radius perpendicular to the axis of rotation. So I'll show you some pictures coming up to help us understand and identify what these things mean. And we'll do some practical calculations. So here I have the 2 calculus versions written out in a printed form that's always neater than my handwriting. And the definitions that dm is, what is this little character here? The funny one before the dv? Rho, right. That's the Greek letter r. Rho dv. What would dv mean to you? Some of you might honestly say, nothing. It means nothing. You're talking a different language than the one I know. But what would it mean to somebody who it means something to?
Is V velocity there? It's capitalized.
V is volume. So what would dV mean?
Area? Mass?
Infinitely small change in volume.
Okay. Go back to what we did when we did the rocket problem. It's an infinitesimal piece of volume. So in our picture, you know, when I talked about the center of mass and the calculation is basically like saying we have a whole bunch of little cubes or little pieces of mass. The dV is a little piece of mass. What's different than the dV piece of mass and the m sub I piece of mass? It's only that the m sub I is some reasonable size, like, you know, a millionth of a gram or something. Whereas the dm and the dv are infinitesimal, 1 over infinity in size. So it's still, we draw pictures to illustrate the idea, and the pictures are going to look the same as what you would do if you had chunks. In fact, I'll show you a rod. We'll do a calculation with a rod in just a moment and see how the dm works out for that. Many times we can use geometry to simplify a 3-dimensional dv into a 1-dimensional area times dx. And so many times we'll try to use that. The last calculation I hope to do today, you'll see that it actually is easier not to do that sometimes as well. So let's move forward. So the uniform rod. Here's a picture, a nice picture to illustrate everything. A uniform rod, and first let's find the dm. So dm is a small piece of mass. So for this rod, it's a uniform rod, which means that it has a constant amount of mass per length. So if I had a rod that was 1 meter long, it would have a mass of some value times that length 1 meter. If it was 2 meters long, it'd have a mass twice as big, that same value times 2 meters. So we call that lambda the lineal density, or mass over length. And so in this case, I can say, well, my dm is just equal to lambda dx, where lambda is the mass per unit area, and then dx is my piece of area. Now to see that in picture, you see here the green rod, and then there's a section of length dx that's black. So that green rod has area dA, but more importantly, it has this lambda, the lineal density, which is the mass on that dA. And so the total mass enclosed by that box is going to be the lineal density lambda multiplied by the width of that box, dx. And so here we just have dm is equal to lambda dx, which is written on their picture. And now let's go ahead and find where the center of mass is. Who can tell me where the center of mass of this uniform rod is going to be? At the center, L over 2. Okay, so we know the answer. It's not like this is a tricky calculation. But to find the center of mass, using our equation, we would have now, my integrals do need units. I need to know what my starting x will be and my ending x will be. Where would be a convenient place to put the origin?
The left.
At the left. In fact, the picture already shows it there. And so that means I'm going to start at the 0 at the left, end at the right, which is a length L away. And so I'm going to be going from 0 to L. Now I need to substitute in my dm's. 0 to L of x times lambda dx on top over integral 0 to L of just lambda dx on bottom. Now you can see right away what's going to happen with those lambdas. They're going to cancel. And so when I do my math, I will first cancel those two lambdas. I have integral of x dx. What's the integral of x dx, friends? X squared over 2. And I have my limits from 0 to L. On the bottom, just integral of constant dx, that is x. Once again, with my limit 0 to L. And so that gives me L squared over 2 minus 0 divided by L minus 0. Sometimes I get really long and explicit. I think we can all see that we could just cancel an L here, and it's L over 2, just like you knew. Now that's how we would do a calculation if we had a uniform density. What if it wasn't uniform density? What if, for instance, we had something that had a linear increase in the density as you go along? So B is some constant. How would I find the center of mass now? You can say, Anne. Do it again, except now the lambdas can't cancel because the lambdas aren't constant. Right? I'll still have a lambda on top and bottom, but if they're not constant, I won't be able to cancel them. So if I use this now, I'm going to have, for my center of mass, that. Now my b's will still cancel. Hooray, I have something that cancels. But going through and doing my math now, I have the integral of x squared dx over the integral of x dx. Integral of x squared is x cubed over 3. Put in my limits, and that's going to be L cubed over 3 on top. Bottom, x squared over 2, put in my limits, that's going to be L squared over 2. And so now if you look at that, the center of mass would be L times 2/3. The center of mass moved farther toward the end of the rod if I had the lineal density increasing with length. Does that make sense? It makes sense because you have more mass farther away, hence it should have the center of mass farther away. Now that fraction 2/3, you have to actually do the math to come up with the fraction 2/3. You can't logically say, oh, it must be 2/3 out. You have to actually do the math. So that's an example of doing center of mass, a one-dimensional example. Rod is one-dimensional. Now let's go back and do the moment of inertia of this rod. Now the moment of inertia is always, just like torque, calculated about an axis. So choose an axis for me. There are two obvious axes. Choose an axis that you... I gotta look back. Oh, the picture's up there. Okay, about the y-axis. I was afraid you'd said about the x-axis. Well, no, I didn't want that one. Okay, about the y-axis. If I want to find the moment of inertia about the y-axis, then I would have to say, let me do a copy this picture onto the next slide. Okay, so there's our figure once again. So we're going to find that's a very interesting way of spelling axis. My brain got to the S when I was writing the X, then I tried to rewrite the X, and then I wrote the X where the S was supposed to be. In case you're wondering how things went so horribly wrong in a four-letter word. So find the moment of inertia, I, about the y-axis. I is the symbol for moment of inertia. I said, in my brain, find moment of inertia, I just wrote I. It's a problem, I just get used to the symbols, but you will too. If I wanted to be more clear, I could have said, let's find IYY, which moment of inertia is actually a tensor. You have to have two subscripts. It's a, yeah. We don't know about tensors, right? So we'll leave it at that. If I want to find the moment of inertia, then my equation is I is equal to the integral of r perpendicular squared dm. And so my r perpendicular, what is the perpendicular distance from the y-axis to any piece of mass in my picture? So I identify r perpendicular equals x. I always do this separately. I identify what r perpendicular is, and I identify what dm is. Now we've just been doing this. We'll do it for the uniform rod. So dm is just going to be lambda dx, excuse me. I identify these so I can plug them in and do my work without issue. So going to do my work, I have the integral of x squared lambda dx. My limits are going from 0 to L. That's a pretty simple integral, right? Just take that, and that's going to be L cubed over 3 lambda. Now you look at that, and it doesn't feel very fun to me. What we generally like to do is make a substitution and put it in terms of the mass of the rod. So what's the mass of the rod? How can I find the mass of the rod? What would be the general calculus equation to find the mass of the rod? Density times volume, but the calculus equation. The integral of, by definition, m is the integral of dm. I'm doing it this way not because it's the only way of doing it. I wrote the m and then hit something. Not because it's the only way of doing it, but because it's the way that conveniently plays into us learning the calculus of these problems, giving us yet another example of just putting in that dm. So m is lambda L. So if I take my moment of inertia and write it in terms of the mass, I will divide out 1 L and 1 lambda, and I will have this is equal to m times L squared over 3. Question, Michael?
Are we treating lambda like a constant?
Lambda is a, yes, I'm going back to lambda as a constant. Thank you. Yes. Yes, because I had done a problem where it wasn't just previous to this. That's a good question. So here we found the moment of inertia about the end of the rod. How would this have differed if instead of the end of the rod I had chosen the center of the rod? Would it be bigger or smaller? Smaller. Why did you come up with smaller?
It's closer to the axis of rotation.
Okay, the mass is closer to the axis of rotation. It's still the same mass, but it's distributed closer. So let's now do that calculation. So I'm just going to change to rotate about the center of the rod. So if I rotate about the center of the rod, everything's going to stay the same in terms of r perpendicular is equal to x. I'm just going to change my origin so that I have this here that I'll call y prime. And now my x goes from minus L over 2 to plus L over 2. Right, just shifting my origin to the center. It's the easiest way to do the math. And so I'm going to have exactly the same integral, but it's minus L over 2 to plus L over 2, x squared lambda dx. So now I'm going to have integral of x squared. I'm going to write this out explicitly. Lambda times lambda over 3 times x cubed, lower limit of minus L over 2, upper limit of L over 2. If you put in your limits, L over 2 cubed is L cubed over 8. And minus L over 2 cubed is minus cubed is a minus, right? I'll answer your question in just a second, Michael. So putting those together, I have equals lambda L cubed. Notice it's 1/8 plus 1/8, which is 1/4. And 1/4 times 1/3 is 1/12. Now, Michael, what was your question?
Well, I was just going to ask where the lambda over 3 came from, but then I remembered
Oh,
I took the 1/3 out
here.
of x3.
Yes. It came from there. So lambda L cubed over 12, now substituting in for m again, I can write this in terms of mass as equals m L squared over 12. So you see there's a difference there, ml squared over 3 versus ml squared over 12, a difference of a factor of 4 by shifting where I had done the moment of inertia about. This is going to conclude my one-dimensional problem, so any questions about the method so far really should ask rather than wait and ask later. Question?
What are the units of moment of inertia?
Excuse me?
What's the units for moment of inertia?
What are the units? Okay, if we just look at the equation, integral of r squared dm. What are the units of r? Meters. So I have meters squared because it's r squared. What are the units of dm? Kilograms. So it's going to be meters squared times kilograms. Right? When you do the integral, you actually aren't changing the units because you had the units of the d thing and the units of the integrand, the part without the d thing, and the total units are still going to be the same. Remember, that's because you're just adding up a whole bunch of things that have all the same units. Other questions? Now, I think the next slide actually says find the moment of inertia about any point around the distance p from D I meant to be along the axis. I'm going to skip over doing this one because we've already done 2 examples. There's really not a need to do a 3rd example of the same problem. And instead go to the flat plate. So here's a uniform flat plate. If it's uniform, that means the mass is distributed equally everywhere. Now, of course, in real life, plates are always 3-dimensional. They have a thickness to them. But I can go ahead, if it's uniform, and treat this as if it has essentially no thickness and has a mass that is distributed as mass over area is equal to a constant. Now, if it was mass over length, we called it the lineal mass density. If it's mass over area, we call it the areal mass density, and we use the symbol sigma. So, how do I find my dm now? Well, dm should clearly be, since m is equal to a sigma, if it's uniform, so sigma is constant, dm is equal to sigma dA. Now, if I have something that is a rectangle, right, 2-dimensional is rectangle, that's a rectangle, I'm going to have to define an x and a y axis. So we have the width there and the length. Which one do you want to consider x and which one do you want to consider y? The width is x? Okay. So I'm just going to follow the suggestion given me by Tori and call the width my x-axis. I'm going to set my origin so it goes, that's the origin, that little black dot, right, where the red line comes out. And I'm going to make my x-axis go out like this, and my y-axis go out like this. And this will be the z-axis that's in red. Now I'm going to find the moment of inertia about the z-axis. By the way, if they're both z, we often will write that as just I subscript z. And for you, that's all you really care about is the iz, the moment of inertia about the z-axis. So I'm going to find the moment of inertia about the z-axis. Well, I need to have some little piece of area dA. And so how do I find this piece of area dA? Well, I have a little piece out here. A little box. Well, that's a horrible box. What I'm going to do is undo. Actually, I can erase it quick with my finger. Zoom in so we can see this better. And make a little box on this. So I'm going to make a little box that has some x component. That's a dx. Can you decipher that's a dx? And it's going to have some y component dy. What's the area of the box that has dx on one side and dy on the other? Dx dy. So I have d area equals dx dy. Now let's go back to the zoom and see what it looks like when it's, I'm happy with it. So my dA is dx dy. That's a double integral. And you might be, oh no, double integral. Oh, it's not the worst thing in the world. We will do this as a double integral though. So to find the moment of inertia, my equation was I equals integral of r perpendicular dm, right? Well, what is my r perpendicular in this case? That is, I better change colors. R perpendicular is that there. What's it going to be? Question?
R perpendicular
Yes, squared. Wow, that's a mistake on my part that if I don't correct now, I probably forget, and we end up being all over the road eventually. R perpendicular. What would R perpendicular be in my picture here? I have my R vectors there. It has an X component and a Y component. Yep. There's our X and there's our Y. So we're going to have the R perpendicular. Hello, Chad. Is the square root of X squared plus Y squared. What about DM? We have all the pieces written here. DM is sigma dA, dA, dx, dy. So what is DM? Sigma dx, dy. So I have my pieces to plug in, so now I'm ready to make my integral equals the integral notice it's actually R perpendicular squared, and R perpendicular had a square root. So when I square the square root, I'm just left with x squared plus y squared. Question, Michael?
Where did you get your R perpendicular from?
Okay, R perpendicular came from, and I'll zoom in again. I'll zoom in so I can fix my picture so it's clearer. We have this distance here was y to go out, and this distance here was x. And so we have that little piece, dA, that is at coordinates x comma y. And r is the perpendicular distance from this red line, so the distance in the plane going out to that point that's x away in the x direction and y away in the y direction. So we just use the Pythagorean theorem, since this is a right triangle, that the hypotenuse is the square root of x squared plus y squared. So I have my R perpendicular squared is what I have in parentheses right now. And then for my dm, I have sigma dx dy. Well, since I have dx dy, that means I have to have two integral signs. One for x, one for y. There, second integral sign. You will find different teachers that do things differently. I like to put an integral sign and have the d that goes with it right next to it, for the simple reason that I can make sure I have the limits. I know if that's the limits for x or the limits for y. So I wrote it like this. So I put my dx dy there, and then I have the rest of my integrand, which is x squared plus y squared sigma. So looking at my figure, what is the extent for x? What's the minimum value x has and the maximum value x has? Right. So for my x limit, I have minus w over 2 to w over 2. And what about the y? Now I have two integrals, and I just simply choose which one I'm going to do first. That's not my finger. It thinks my finger is touching, which means, of course, it's not going to work with my finger, but it'll still work with the stylus, so we can still continue working. Which integral do you want to do first? Okay, dx, she says. So the dx integral, I'm going to put then equals integral minus L over 2 to L over 2 dy. And then inside this box, I'll do my integral on x. So I have x squared dx. Oh, let's put the sigma out here. It's a constant. What's the integral of x squared dx? And then I have y squared dx. What's the integral of y squared dx? It's just xy squared. Because in integral of dx, the y is a constant. Nice job. Let's recognize my finger again. That's a start. Got to put my limits in here, minus w over 2 to w over 2. When I put in my limits, for the upper limit, I will have w over 2 cubed, which is w cubed over 8. And of course, what's 8 times 3? So I have w cubed over 24 plus w over 2 y squared minus, putting in my lower limits. But when I have minus cubed, what's minus cubed? Still minus. So I have minus and negative, which means it's going to be a plus. And again, it's going to come out to be w cubed over 24 due to symmetry. This is just an x. So again, minus a negative w over 2 makes it a plus. So the top two terms were the upper limit. The lower two terms were the lower limit. You see they added the same amount for both. And so now I will write, I am flying through the paper today. Well, the virtual paper, if you will. I will take this and rewrite it at the top of the next page, assuming that I can scroll. Actually, it looks like there was a little more to write. So there I just combined the terms. 1/2 plus 1/2 is 1. 1/24 plus 1/24 is 1/12. Now we have to do the second integral. So now we'll do the dy integral. Have to put in my limits again. Now, as you can see from what we just finished doing, this one here, the upper limit puts in an L over 2, the lower limit puts in minus a negative L over 2, so another L over 2. So I'm going to get a combined multiply this term by L. The second one, just like before, upper limit's going to give me an L cubed over 8. Lower limit minus a negative L cubed over 8. So I'm going to be multiplying by L cubed over 4. 4 times 3 being 12. When you look at it like this, there should be a fair amount of relief that it's symmetrical between W and L. If it wasn't symmetrical between W and L, then we'd have a serious problem since we had a rectangle. There was nothing special about X versus Y. And so now I'll rewrite that finally as sigma over 12 WL times W squared plus L squared. Wow, there was just not enough room for that. Close enough. Now, what is the equation for the area of a rectangle? Width times length. So that means the mass, which is sigma times the area, is sigma width times length. So this is equal to mass over 12 W squared plus L squared. So there we found the moment of inertia if you rotate it about the center. A little more complicated, right? It required a double integral. It wasn't a very hard double integral, all things told. It wasn't, I didn't have any crazy limits where limit of A depended on B or something like that, limit of X depended on Y, which you'll cover in your calculus classes. But it still required us to do a second integral. I see I have 8 minutes left. So let's get to, not that, that. Find the moment of inertia of a uniform disk. About the center again. So I'm going to find the IZ. Now you see they found 3 different ones. IXX or IYY. That's the moment of inertia about the x-axis or about the y-axis. And then we have IZZ, the one I'm going to find, and IZ prime, Z prime, when they put the Z prime on the edge of the circle. The first 2 are the same integral, basically. I'm interested in doing the one about the center because, well, that's the one that makes me happiest. So if I'm going to do about the center, I'm going to find IZ equals integral of r perpendicular squared dm. It's uniform, so my mass is equal to sigma times area. dm is equal to sigma dx dy, just like we did before. So what do I have for r perpendicular? It's what? Well, if I have some point out here at x and y, it's what? The same as last time, yes. Square root of x squared plus y squared. And my dm is the same as last time, sigma dx dy. What's different? It's a circle. What difference does that make? My integration limits. Now when I do my integral, nice job. With it not recognizing my finger correctly, I'm having a very hard time erasing. Eraser tool to the rescue. So I have that integral, but now I have to worry about the limits. And I'm going to do my x limit from 0 to the radius. I used a capital R. I like to use capital for a constant radius and lowercase r for something that's varying, if you want to know my preference. Actually, it doesn't go from 0 to r now, does it? It goes from minus r to capital R because the x is going to go from one side to the other. What about the value of y? Let's say x is out here. How big does y go? If it's all the way out here, how big does y go at that point? It goes from 0 to 0, doesn't it? Right, if I'm all the way at this side, then my y has no expanse to stay on the circle. But if I come down to here, then I could have my y going from there to there. And so I'm going to have to use a little bit of trigonometry. This side here is capital R. This side here is y. This side here is x. And say, okay, for my y extent, it's going to be y here is the square root of r squared minus x squared. So it's going to go from minus square root of r squared minus x squared up to square root of r squared minus x squared. That's where the double integral gets more complicated because my limit now has the variable in it. So by choosing, I already chose which limit I was going to integrate first by saying my x, I'm going from minus r to plus r. And that meant my y is going to have to depend on the x. So I do my y integral first. And after I do my y integral, I do my x integral. Now, if you look at this, you can say, I don't want to, right? I mean, isn't that what you would tend to think? I don't want to? That's what I would anyway. So instead of doing this, we can go to a different type of coordinates. What type of coordinate system is more convenient for integrating a circle? Polar coordinates. So with polar coordinates, sometimes recognize finger doesn't. Shift to polar coordinates. In 3 dimensions, that would be cylindrical coordinates. So with the polar coordinates, what is dA for polar coordinates? Maybe I need to start with something before that. Polar coordinates are defined, instead of having x and y, you have r, and I'm going to call the angle here phi. I'm going to call it phi because of this, because that makes phi have the same meaning when we go to spherical coordinates.
Is the polar coordinates, you measure it in radians, or do you measure it in?
The angle, yeah, you should measure in radians. But what is dA going to be now? We have a little piece out here. On this side, it's dr. On this side, it's r d phi. So what is dA? How do I get r d phi? Because the arc length is radius times the angle. So it has some angle d phi, and so the length is r d phi. So what would dA be?
What area are you taking? What is that?
The area of this box. Here, I'll color in the box in a different color. The area of this green box. Now that green box is a length of dr and a width of r d phi. Or r d phi if you want to say it that way. So, yes, it's r times dr d phi. So my dA is a little more interesting. It's got an extra piece on there. It still has to have units of area that is meters squared. So if you look at that, what are the units of d phi? You just said radians, but radians really are unitless. So there's no units in the d phi. dr has units of meters and r has units of meters. It still has units of meters squared. So that's my dA. What about my r perpendicular now? Well, now we made it easy because r perpendicular distance from the center out is just the radius r. And so now my integral becomes I about the z-axis is equal to the integral I need to put this in the proper order. R squared times sigma r dr d phi. Right, this here was my new dm. I didn't write my new dm, I just put dA. dm is equal to sigma dA equals sigma r dr d phi. So now I do this integral. Notice I still have a double integral. I have r and I have phi. What is the limit for r? Going back to my picture. How big is my radius going to go? From actually only from 0 to capital R. Only from 0 to capital R because the radius can't be negative. What about my angle? I'm doing a complete circle, so what's my angle going to go from? Yeah, that was not very difficult. Now the way I like to write this is equals integral from 0 to capital R. Notice I have r squared times r, so that's r cubed dr. Integral from 0 to 2 pi d phi, and put that sigma out there all alone. These two integrals are completely independent. By changing my coordinate system, I was able to take dependent integrals and make them independent. So I have just two single integrals. What's the integral from 0 to 2 pi of d phi? 2 pi, right? That ain't brain surgery or rocket science or anything else. What about the integral from 0 to capital R of r cubed dr? And of course the sigma stays there. So this is equal to, notice I have a 2 pi here and a 4 there, so I'm going to make it pi over 2 r to the 4th. Well, oftentimes we like to put it in mass, like I said, and the mass here is sigma times the area. Area of the circle is pi r squared. So if I replace a sigma pi r squared with m, that's going to be equal to m over 2 r squared. That calculus was very simple because I changed to cylindrical coordinates. Yes?
So why are those independent?
They're independent because I can separate, so I only have phi stuff here and I only have r stuff here. Right, with the one that I had up above, I had x and y here, and there's no way to separate those, so I have just x stuff and just y stuff. And with the limits dependent, it was a nuisance. Now, I see my time has passed. The next step, if I'm going to do a sphere, I should use spherical coordinates. And if you haven't seen spherical coordinates, the spherical coordinate, here is how you define the phi is going all the way around the circle. It's an azimuthal angle. The theta is the altitude angle. Theta only goes from 0 to pi. If theta went from 0 to 2 pi, you'd have an angle going all the way around this way and an angle going all the way around this way. You would be covering the entire volume twice. So theta goes from 0 to pi. Phi goes from 0 to 2 pi. And of course, r goes from 0 to the radius, generally speaking, if it's a sphere. And then we make a little piece of volume dv. So this brown is a piece of volume dv that has this axis here is dr. Or that side. This side here is r d theta. And this side here is r sine theta d phi. And so to get the volume, of course, you multiply the three sides of the cube. And so you have r sine theta d phi times r d theta times dr. So the d volume element is r squared sine theta d theta dr d phi. I don't have time clearly to do the moment of inertia for a sphere, but once again, if you do it in spherical coordinates, it separates out. It's very simple. If you do it in Cartesian coordinates, x, y, z, named after Rene Descartes, then it's a fairly complicated integral that I, in preparation, decided I am not going to do this. Actually, no, I take that back. I did do it. It's a difficult integral. You want to make your life easier. So you should be able to do these cylindrical coordinates and spherical coordinates to make your life easy. In all cases, it could be done in Cartesian, but it's much, much harder. Well, in the appropriate cases, it's much, much harder. Okay, we're out of time. If you have more questions, you can ask them, but I can't hold it. I won't hold you.